This series of lessons will teach you about the many aspects of the stall, an aerodynamic phenomenon which can result in loss of height and ultimately loss of control if not correctly recognized and handled. Such a situation would obviously be potentially very hazardous at low level on the approach or after takeoff. It is vital, therefore, that a pilot should be able to identify the signs and symptoms of stalls in any configuration or stage of flight, in order to prevent or recover from a stall with minimum height loss. You'll be taught how to do this during your flying training, but these lessons will give you the theoretical knowledge you will need to understand how and why stalls happen. Different types of aircraft exhibit different stalling characteristics, some less desirable than others, but all should give the pilot some indication of an incipient stall. Airworthiness authorities specify the minimum stall qualities that an aircraft must possess. Reference will be made in the course of the lessons to such regulations for training purposes, but you should note that these requirements are occasionally subject to change. The coefficient of lift, or CL, of an aerofoil increases with angle of attack up to a maximum CL max. Any further increase above this critical angle of attack or stalling angle will make it impossible for the airflow to follow the upper contour of the wing smoothly. The flow will separate from the surface, causing CL to decrease and drag to increase rapidly. Since the CL max of an aerofoil corresponds to the minimum steady level flight speed, the 1g stall speed, it is an important point of reference. The stall, then, is caused by airflow separation, which occurs either when the boundary layer has insufficient energy or the adverse pressure gradient becomes too great. If we look at a sequence of an approach to the stall, we can see that at low angles of attack, virtually no flow separation occurs before the trailing edge, the flow being attached over the rear part of the wing in the form of a turbulent boundary layer. As angle of attack, or alpha, is increased, the adverse pressure gradient increases, reducing the kinetic energy, and the boundary layer will begin to separate from the surface at the trailing edge. Further increase of alpha makes the separation point move further forward, and the area of the wing that is generating a pressure differential, and thus lift, becomes progressively smaller. At alphas greater than the critical angle, which will depend on the wing planform, the extremely steep adverse pressure gradient will have caused so much separation that the wing can no longer generate enough lift to support the aircraft's weight, and the wing is stalled. It is important to remember that the angle of attack is the angle between the chord line and the relative airflow. Therefore, if the angle of attack is increased up to or beyond the critical angle, an aeroplane can be stalled at any airspeed or flight attitude. If we study the lift curve shown in this sequence, it can be seen that the increase in CL is linear over a large proportion of the range of alpha up to the stall. But as the effects of separation begin to be felt, the curve begins to flatten. Eventually, CL reaches a peak and then drops at an angle steeper than the rate of increase. The alpha at which it reaches its peak is called the critical or stalling angle of attack, and the corresponding value of lift coefficient is CL max. Most aeroplanes will stall at around 14 to 16 degrees alpha. Stall characteristics vary with different kinds of aircraft, but there are common factors which may occur with all aeroplanes. For modern aircraft, during most manoeuvres, the onset of the stall is gradual. The first indications may be provided by any or all of the following. Flight controls less effective than usual. Speed low and decreasing. Nose attitude higher than normal. Light aerodynamic buffet. Or the operation of a stall warning or stall prevention device. If the stall is allowed to progress beyond the incipient stage, any one of the following is symptomatic of a fully developed stall. Wing drop, nose drop, heavy aerodynamic buffet, or a loss of height. These symptoms form part of the formal stall recognition conditions described shortly. The behaviour of various types of aircraft at the stall is covered in more detail later, and recovery from the stall is described in the next part of the lesson. If a stall occurs, either incipient or fully developed, the principal action that must be taken is to reduce the angle of attack below the critical angle to decrease the adverse pressure gradient. This action may consist simply of releasing back pressure on the control column or moving it smoothly forward until the wings are unstalled. Excessive forward movement of the controls would lead to an unnecessary height loss during recovery. The use of full or maximum permitted power is usual during stall recovery to minimize height loss. As the angle of attack reduces, the airspeed will increase, and at a safe margin above the stall speed, any lost height can be regained by moving the control column back. Pilots should be careful not to pitch up too quickly, as this may restall the wing, even at a higher speed, which is known as a secondary stall and is covered in detail later in this series of lessons. The rudder should be used with great caution at any time when stalled or close to the stall, because of the possibility of causing a spin, on which more later. It is safer to use the rudder only after the wings are unstalled, and then only to prevent further yaw if a wing has dropped because it has stalled slightly before the other. It is generally safer only to use the ailerons to level the wings, also once the wings are unstalled. On swept-wing aeroplanes, the ailerons can be used to correct a wing drop, coordinated with a small amount of rudder, because design requirements for stall characteristics demand features promoting early wing root stall. However, the rudder on modern jet transports is very powerful, and excessive use can result in over-controlling, or even, in extreme cases, structural failure. At the low speeds normally associated with stalling, dynamic pressure is at a low value, and greater deflection will be required to achieve the same response as that found at a higher speed. The controls will also feel less responsive, as mentioned earlier in the lesson. If an accidental stall should occur, it is important that the recovery is effected before the process develops too far, with a large wing drop giving a high rate of descent or possibly leading to a spin. Moving a control surface alters the chord line and hence the angle of attack. An aircraft may have one wing which is less efficient than the other and stalls slightly before it, causing a wing drop. Trying to lift a dropping wing with aileron will increase its angle of attack further, taking it deeper into the stall. At the same time, the upgoing aileron on the opposite wing will decrease its angle of attack, possibly unstalling that wing, which produces more lift and exacerbates the roll already made worse by the changes in effective angle of attack. The moral of this is that ailerons should be used with great caution when close to the stall. Swept-wing aircraft basic stalling requirements, however, are designed to enable safe use of the ailerons as far as stall recognition, with small amounts of rudder, if smoothly applied, to coordinate with the ailerons. Various means of achieving this capability are discussed later. The use of rudder has already been mentioned in the earlier section on stall recovery, with its attendant risks. A coarse application of rudder before the wings are unstalled to pick up a dropped wing, but inadvertently in the wrong sense, in the direction of roll, could put the aircraft into a spin. Even if the rudder were applied to oppose a wing drop, it would require a large rudder deflection, which could well cause a spin in the opposite direction. Taken with the aforementioned restrictions on the use of the ailerons, these factors would suggest that the ailerons and rudder should be kept neutral until the wings are unstalled, and only used when the aircraft has reached a safe speed margin above the stall. A formal standard of stall recognition is established to determine when the behaviour of the aeroplane gives the pilot a clear and distinctive indication of an acceptable nature that the aeroplane is stalled. These acceptable indications of a stall, occurring either individually or in combination, are 1. A nose-down pitch that cannot be readily arrested. 2. buffeting of a magnitude and severity that is a strong and effective deterrent to further speed reduction. And 3. The control column reaches the aft stop, that is, full up elevator, and no further increase in pitch attitude occurs when the control is held fully aft for a short time before recovery is initiated. The following section of the series of lessons deals with stall speeds and warning and prevention devices.